Professor Jeff Smith, you're with the University of Technology's School of Physics and Advanced Materials, and my understanding is that you're studying thermal comfort in buildings. Can you tell me what that is?
Well, thermal comfort is about achieving conditions where humans feel comfortable and can work well and enjoy get on and do the things they want to do without feeling uncomfortable, such as it's too hot or too cold, or the humidity's too high, or it's too stuffy, and so on. So all those issues are what we're looking at, but in particular we're looking at the impact of roofs at the moment on that.
And what are you specifically researching?
Well, we're researching coatings and treatments for a roof that make it reflect more sun and also radiate efficiently.
So what kind of experiments are you doing here at UTS?
Well, we're looking at the performance of structures with different types of roof coatings on them, and also controlled airflow and variations in the insulation levels, to see the relative impacts of all these factors.
And what are the factors that come into consideration there?
In the building itself, we monitor the airflow and the temperatures. That's straightforward. But it's the outside, the environmental energy flows we monitor with the solar radiation, we monitor the atmospheric radiation, we monitor the wind speed, and we monitor humidity. And the instruments we do that, there's a variety of instruments needed to do that. The Weather Bureau does these things as well, of course, but we do them right where our building is, because it's very important to know what's happening at the building.
I also understand that you've had to invent an instrument.
Yes, well, it's not so much invent, but we've had to set up an instrument that enables us to monitor exactly where the thermal radiation is coming from, and if you like, map the sky or the field of view, including trees, neighbouring buildings and so on. So we actually have an infrared detector that scans the whole sky hemisphere. And if there's clouds in some part of the sky and not another, and so on, all these, and how thick as you go down, as the atmosphere gets thicker and radiates more. So we can take count of all those factors, but it's very important for which part of the building cools and which part doesn't.
It sounds pretty impressive.
That's quite good, yes, to get on top of all of this.
Where are you hoping this research is going to end up?
Every building in Australia now has rules about how it's built in terms of energy it's used. And the issues of cool roofs and so on is not properly catered for in those yet. There are advisory things, but the impact is not properly integrated. Secondly, I'd like local councils to take note of this, because that's part of the building codes. But secondly, there are things you can do in the whole precinct, because the air's colder. Guess what? Two things happen. Your air conditioners, when you do need them, you need them less, work better, and it's much more pleasant outdoors.
It's interesting to see how something so subtle yet complex can have real life benefits.
Yes, it can, because it doesn't cost much to change the properties of the roof and roads to reflect more sun and give off more radiation. And the result is that the buildings are more comfortable to live in without using air conditioning, or using a lot less air conditioning. That the precincts, the areas around the buildings, especially if there's enough, get cooler, and that is nice as well, and also reduces air conditioning loads further because the air is cooler. Secondly, if enough cities and towns and everything around the world reflect more sun, then we offset a lot of the warming of the CO2, and that is something that people don't understand. They think it's all about CO2, but it's also about the amount of heat we directly put in the atmosphere.
Professor Jeff Smith, thank you so much for your time, and let's hope that we see more cool roofs around Australia and the world.
Thank you. Yes, we hope so.